What? We lost the diamond? I'll get Team HAPI on the case.
On my way.
Alright team, I've assembled you here for a covert mission. We need communications and a device that measures light, temperature, and distance. We roll out in 24 hours. And remember, be discreet.
Boss asked me to give you a high alert since you stole that diamond. Come, put us under arrest!
I designed the mechanical components for the tie knot with the integrated camera, the OLED watch with a dual housing microcontroller setup, and the 2-finger ring with a hidden distance sensor. All of our printed parts were produced in a PLA on a Prusa Mark III 3D printer. In addition to 3D printing, I also laser cut out our HAPI agent badges and include a QR tag that links directly to our team's files. We follow the engineering design process by first defining the needs and constraints provided, brainstorm potential devices, and narrow them down based on feasibility and available time. Here are some early concept sketches of our devices. I used SolidWorks to model the parts that met the criteria and integrated our team logo across all devices. I stuck with a hexagonal shape to maintain visual consistency, and once the prints were complete, we tested for form, fit, and function. I faced numerous challenges during fabrication. For example, the tie knot cover of our first design was too fragile and it broke during use. I tried to mitigate the problem by spreading the load across 2 pins, but that also failed under stress. So the final iteration, I increased the thickness and the infill of the clips, and that seems to have fixed the problem. I also had troubles with the watch band. The original concept used removable 3D printed links for size adjustment, but the tolerance were too tight. In the end, we ended up ditching the links and redesigned the strap out of Velcro and bungee cord, and that seems to have fixed the problem. I would have loved to integrate the servo hatch to conceal the camera lens and switch to smaller perf boards to reduce the bulk and improve the user comfort. This project really pushed my skills in both design and rapid iteration and gave me a clearer sense of what it takes to bring a functional prototype from sketch to a field test.
What is it on your wrist?
Oh, this? This is just my watch.
Oh really? Okay, you're free to go now.
Switch to data mode.
For the coding design, I used an MQTT broker to have each sensor Pico publish their data, and I had a display Pico subscribe to each of the topics that carried sensor input. I also had the front end subscribe to the broker via Socket.io in order to display data on the website. For the AI camera portion, I fetched the image from the URL generated by the provided camera library and sent it to OpenAI. The image was hosted via Express in order to accomplish dynamic rendering of new images. The speech file generated by AI was similarly served by Express to the front end and incorporated into the website. Some challenges I faced during this project were debugging Socket.io and getting the images to update dynamically at runtime rather than needing to be present at compile time. Some iterations this project went through were trying multiple ways of connecting to Socket and debugging, and eventually learning that console.log in React goes to the browser console rather than the terminal. I tried various ways to access and update the image dynamically with just a file access, but eventually settled on serving the files with Express, which was already a dependency of the project, which is convenient. I also went through multiple iterations of the watch code and made sure to implement non-blocking timing on the functions that I was calling repeatedly in a while loop. The next steps for me on this project would be to add more sensors and make the OLED code more robust. If I could do it all over again, I'd probably get more involved in the circuits and make sure the soldering was more solid. But overall, I learned a lot about microcontrollers and how to make code interact with hardware.
Where's the painting?
Oh.
Okay, so we have the AI.
This is Monet. Claude Monet.
Use your cameras, use your cameras.
What?
Lily's Bridge, or the Water Lily Pond series by Claude Monet, a renowned French impressionist painter.
Okay, 4 minutes left.
Are you getting temperature readings to unlock the door? Because it's getting hot in here.
Is light supposed to be negative?
Negative number.
Expose.
Oh shit, something sparked.
Is that the circuit? That's
Yeah, leave the wires over here. Dang,
A little bit about the temperature humidity set. The main function in this circuit will provide a temperature and humidity readings via single wire communication protocol through ground pin 6. So we see here in the circuit that the positive will be connected to 3.3 volts, and then data will be connected to ground pin 6. I made sure to make it compact enough, keeping in mind the design of the tie and the limited space I have, so I put ground as close as possible to 3. In this circuit, the light distance resistance 1 pin is connected to 3.3 volts, and it is combined with the 3K ohms resistor on ground put 26. It is an analog pin, so we made sure that we use analog ground when connecting the 3K ohm resistor. To demonstrate on the Pico how close 8 analog ground and the ground put 26 were on the Pico, emphasize how compact we wanted this design. My main challenge was the temperature and humidity sensors, making everything compact. The second challenge was over soldering, covering the GPIO pins on the Pico. For example, 3v3 is blocked, VSys is also blocked, ground pin 3, and ground pin 6, and at the time I hadn't had anything connected. I learned how to manage difficult wires, especially the ones that were easily to pull out, as well as the ones that frayed, for example, here and here. I learned how to recover from soldering mistakes, so I emphasized the importance of planning component placements before even soldering and making anything permanent. Onto the photoresistor, some challenges was miscommunicating with my team about the sensors and where we wanted them. My second challenge was measuring the photoresistor, not only the voltage, but also how long I wanted it and how compact I wanted it as well. My third challenge was short-circuiting at the end. What I would have done differently is better component testing before circuit integration, use the multimeter to verify photoresistor values in different lighting conditions, double-check voltage divider calculations before even soldering. Lastly, clear team communications about the sensor specifications and requirements.
And the light is 0.31. Temperature is 78.8.
And what's the constant?
It should be 70, sorry. It should be 70.
7.
It should be 70.
70.
Intruder alert. 15 minutes to shut down.
Security guard,
The distance sensor is also known as the HCSR04 ultrasonic distance measuring sensor module. How it works is that the trigger pin sends out a pulse of 10 microseconds. The pulse hits an object and then returns. The echo pin then receives the pulse. The distance is then calculated from the time it took for the pulse to return. Just to clarify, the trigger pin is an output pin and the echo pin is an input pin. For the OLED display, the model we use is the SSD 1306 OLED display. How it works is that the Pico 2W sends out clock pulses via the SCL, also known as a serial clock, and the OLED sends and receives data in each pulse through the SDA, also known as serial data. In our case, because the battery was 3.7 volts, that's the one that we used. So the bottom of the tie was made from foam and cloth. The cloth is sewn together using blue thread, and there is a gap which is closed by Velcro. I figured out how to make the messages scroll for more effective communication. I also added the time to the watch by synchronizing it to NTP, Network Time Protocol. This is the same time used by our computers and other devices to have the same time. I also coded it to allow the watch to display sensor data. It was scrolling from right to left. Challenges. For the OLED, the NTP for the OLED would not synchronize. The lettering kept on overlapping on the screen. For the tie bottom, I had not realized that the cardboard was provided inside. I went digging through the dumpsters. Iterations. For the OLED and distance sensor, originally they were on the same Pico. However, we had to switch to different Picos after the soldering failed. The OLED also originally had a physical button that switched the spy mode and the watch mode. However, it got transferred to the digital one. Also, the OLED failed because of weak soldering connections. I used the stripped wires. However, the stripped wires were really weak and kept on falling off. I would definitely use the header pin wires. Key takeaways. So I learned that communication between a team and the division of roles is very important. And most importantly, simplicity is the best.
40.8 or 41 now. So 40. I'm gonna assume it's 40.
Woo! Oh fuck! I forgot. Okay, no, ignore that. Ignore that.
It's MONET. Oh, here's the later too. Where's T?
Go unscrew the pen.
Go
Right here?
Where's the pen?
This is the laser
Yeah,
part. Yeah.
This is the pen.
Unscrew it.
Laser security camera.
Is that the security pen?
There's
Guess
a
you
laser.
can't tell
There's a
us.
laser.
Right, and there's
Yeah.
3 dots.
Well, we gotta be right.
There's 3.
Oh, no, that's.
Oh, the one on the right. Hit the one on the right.
My hand might be too shaky. Somebody else.
This guy here. There it is.
Oh, that's cool.
There's key.
And then I would
And then you're supposed to unlock it. Yeah.
Yeah, we win.
All right. Yeah, you guys. Damn it! I fucking. That's on me. But you would have been able to unlock it, and then boom, there's your diamond.
Yeah.
All right. Congrats.
Thank you.
Congrats. You guys are the best team that I've gotten so far.
Really? Even with like 3 out of 4 of our sensors.
Okay. Oh. Okay.
Thank you.
Okay. Good job. Good job. All your batteries here.
We got the diamond.